this video, we are going to discuss about low voltage and high current voltage regulator using IC723. It is also called as LVHC. So here, previously we have discussed about low voltage and low current. So it will produce current up to 150 milliampere, right? So here, the current get boosted by adding this extra transistor, right? Between this, the base is connected to the V out, and the collector is connected to VC, and the emitter is connected to the current limited terminal. This transistor is used to improve the current source capacity. Okay, so uh, instead of getting the IL max, since it is a the gain of the transistor is beta. Okay, so I'll get the output is towards this one, right? So the I naught is equal to beta times IL max. So beta is a very large value, right? It's up to more than 100. So you will get the current is equal to I naught is equal to beta times IL max. So thereby you will achieve the current boost. Next, let us discuss about IEC723 as a high voltage low current circuit. So this is a typical circuit connection diagram. So in this you can see the V inverting input, that is equal to V naught into R2 divided by R2 plus R1. Okay, so thus uh, V inverting, that is V in, that is equal to V reference. Therefore V naught I can write it as R1 plus R2 divided by R2 into V reference. So I can write V naught is equal to 1 plus R1 divided by R2 into V reference. So this circuit is capable of supplying a regulated output voltage between the range of 7 to 37 volt with a maximum load current of 150 milliampere. And I already told you this non-inverting terminal is now connected to the V reference through the resistance R3, and see the circuit. Then if you see the value of R1 and R2 are adjusted in order to get the voltage reference at the inverting terminal at the desired output. Okay. So based on the value of R1 and R2, the V naught get changed, and you can see the RSC is connected between CL and CS terminal as before, and it provides the short circuit current limiting. The RSC is equal to 0.6. 0.6 is a voltage across the VBE divided by I limit. The value of the resistance R3 is given by R3 is equal to R1 parallel R2, that is equal to R1 R2 divided by R1 plus R2. So next we will discuss about IC723 as a high voltage high current circuit. So here you can see this is similar to that of the current boosting. Here I have added one transistor T1. Okay. So this external transistor Q is added in the circuit for high voltage low current regulator in order to improve its current sourcing capacity. So it will provide the output voltage varies from between 7 to 37 volt. This transistor Q will increase as the current sourcing capacity. Thus the IL max is greater than 150 milliampere. So I can write that V naught is equal to R1 plus R2 divided by R2 into V reference. Okay, so I can write V naught is equal to 1 plus R1 divided by R2 into V reference. So RSC I can write it as 0.6 divided by I limit. This is similar to that of the previous circuit. Let us discuss about one problem. So design a continuously adjustable power supply for the range of 2 to 5 volt, that is output, with the current limiting of 1 amps using LM723. So since we know that the voltage is less than 7 volt, it is a low voltage, and the current is greater than 180 milliampere. So it is high current. So this is a typical circuit connection diagram. So from this I can write, if you apply the voltage divider rule, I can write V inverting voltage is equal, non-inverting voltage is equal to V reference into R2 divided by R2 plus R1. And we know that the V reference value is 7.15. Always it is 7.15 only. So the output we want to achieve is 5 volt. V naught value is 5 volts, since the V naught value is equal to the V non-inverting value. So if you substitute, I will get 5 divided by 7.15, that is equal to 0.699. So the R2 by R2 plus R1 value is 0.699. Okay. So if the value of the V reference is 7.15, non-inverting value is 5, this must be 2.15, right? So I can write, if the current flowing through this one, if I assume the current flowing through this one is 1 milliamps, this is assumption. Okay, so the voltage at this point is 2.5 volt, this is 2.5 volt, and this is 5 volt. So the R1 is equal to 2.15 divided by 1 milliamps, that is nothing but 2.15 kilo ohm. Okay, so the R2 values are nothing but 5 divided by 1 milliamps, that is nothing but 5K. Okay, so from this I can write R3. What is R3? R3 is equal to R1 parallel R2, that is equal to R1 R2 divided by R1 plus R2. So you substitute the value and find the value of RSC. Okay, that is 2.15 into 5 divided by 7.15 K kilo. So in order to find the value of RSC is equal to 0.5 divided by I limit. If we assume the I limit value is equal to 200 milliampere, if I substitute in this equation, RSC value is equal to 1.5K. So this is nothing but 1.5K. Okay, this is 2.15 kilo ohm, and this is 5K. Okay, the C value also have got. So in order to find the value of RL, okay, so what is V naught? V naught we need to obtain as 5 volt, and the current flowing through this one is 2 amps, that is, sorry, 1 amps. So that is a given problem. Okay, so what is RL? RL value is equal to 5 ohm. Okay, so next I need to find the value of, how to select the value of Q. Okay, so in order to find the value of Q, so you know the formula for beta, right? Beta is equal to IC divided by I beta, IB. Okay, so if I substitute, if I assume IB value is equal to this assumption value, okay, and I need to find the value of IC, right? So the IC value is nothing but IC values 1 amps, right? So you will get if this is 1 amps, if we solve, you will get what is 1 divided by 150. 1 divided by 150 is 6.66. 6.66, that is a beta value. So if I want to find the power dissipation of the transistor Q, the initial the supply voltage is 12, and I'm going to get the output as 0 if it is short circuited into this current value. So what is the current value? Current value is ISC, right? So here the ISC value, I have assumed it as 200. If you see the ISC value is this is the ISC value, I limit value. Short circuit current value, so that is 200 milliamps. Okay, so 12 into 200 milliamps. Okay, so that is equal to, you will get the answer as 2.4 volt, 2.4 watts. So you have to select the transistor, right? So you have to select the transistor. The PDQ values greater than or equal to 2.4 watts, and beta must be greater than or equal to 6.66. Okay, and you can substitute the value. RSC is nothing but 1 point. R3 is also 1.5 K. This is nothing but 12 volt. Even 12 volt. Okay. So this is how you have to design a circuit.